last class we were discussing about some example that is on sum of n numbers on different models, and we discussed on mesh connected computer. We also discussed on perfect shuffle and also then hypercube. Did we discuss on butterfly? Yes. Butterfly also. Now cube connected cycle. Did we discuss that on that? Yes. Yes? Sum of n numbers.
Cube connected is not.
On butterfly is done, right? Okay. Let us do on first cube connected and then we'll go for butterfly. Cube connected cycle. And if you remember, in the cube connected cycles you have right, and this k into 2 to the power k process you divide it into k groups. Each is having 2 to the power 2 to the power k processors, right? So let us also assume that Pij is the processor in the ith group, jth processor in the ith group, and all these processors of the different groups of the same j, they form a cycle. Okay? So this is Pi1, P1j, P2j, P3j, and Pkj. Right? This is the structure. And Pi1j is connected with P1j is connected with one processor of another cycle. Agreed? Which is P1k, something like that, or P1n. Now, in the case of finding the sum, what can you suggest some method? How are you going to do it? So it is a combination of butterfly and hypercube. Okay. So what I want that since it is a combination of butterfly and hypercube, if I consider this cycle is a node, only one node, then similarly you will have so each of them is this cycle. Each of them is a cycle. Then I get a hypercube, right? Now can I use my hypercube algorithms to collapse it and get the results here? Yes or no? Right? This is connected. This node is connected with this node exactly at one point. Okay? So I can collapse it and I can get this data here. Similarly, I can get this data here. I can get this data here. I can get this data here. Then if I collapse this direction, so this data will move to here. This data also will move to here. Right? Now if I collapse this data will move to here. Agreed? Now, if I do that, what problem I may face? Can you tell me? This, one thing remember, this is connected with this node through only one connection. But you observe there are two data are lying here. And these two data is not lying here, it is somewhere here and here. Is it okay? So every time, whatever data you send, you have to add it in that cycle and then bring it to the appropriate position so that you can transmit that data. Is it clear? Any ambiguity here? See, the processor P1J is connected with P1K, right? Now, if you bring this data here, it will come to this P1J. Now, next time you will be collapsing, this is connected with P1 something else, P1L, say. But while you get the data from here to here, you need to bring them into another positions, right? Say for this case, if I have the 3 into 8 processors, so this 3 forms a cycle, this 3 forms a cycle and so on. Now if you collapse the data from this side to this side, this data is lying here. This data is lying here, right? Similarly, this data is lying here. Similarly, this data is lying here. So what happens? You can send only one data, which is added here. But that is not good. You need to get the sum of all these 3 elements. That has to be sent. You understood? Because this contains the 3 elements. So you first make the sum, send it here. So the data is added here. Right? Similarly, you make the sum, send it here, data is added to this processor. Similarly, you send it, data is added to this. Send the data is added to this. Now in this region, this contains the sum of 4 elements. This contains sum of 1 element. This contains sum of 1 element. This contains sum of 4 elements, 1 element, 1 element, 4 element, 1 element, 1 element, 4 element, 1 element, 1 element. Now in this you add it. In this you add it. You get the sum of 6 elements. Sum of 6 elements. Bring it to the appropriate position so that goes up. That goes up. So this contains the sum of 7 elements. This contains sum of 7 elements. This contains sum of 4 elements, this contains sum of 4 elements, this contains sum of 1 element, this contains sum of 1 element. Agreed? Now you add all these elements, and send it to here, that will give you the sum of all 24 elements. So you need little bookkeeping to do all this work. Yes? So what is the time complexity you are expecting in that? You observe at every stage you need in the worst case k additions. Why worst case? That say front side you are making no addition, but this side you make the k additions, which is linearly connected. So you need k, order k times. Then you are collapsing, which takes order 1 time. Okay. Next time again k additions and again order 1 time. So what is the time complexity is coming? Order k log n times, log k times. Right? So order k into log of 2 to the power k, which is k. So it is order k square time. Is it okay? This first k is for adding using the cycle, and then collapsing will be done k times, because 2 to the power k processors, so it is order k square time. Right? So cost is ordered k cube 2 to the power k, and this is nothing but order n log square n, which is a way of factoring log square n. Now the problem is, can you design a cost optimal algo for. So that is the things you have to now think. That is it possible to design a cost optimal parallel algorithm on cube connected cycle? So first you look for adaptive algorithms, and then you find out for what value of P you get the cost optimized algorithm. See, here the load is somewhere else. Load is that cycle. Unnecessarily we are creating or putting additional effort on the cycle, right? So you have to look into that, whether it is possible to design a cost optimal parallel algorithms on cube connected cycle. Now the next one is the sum of n numbers on butterfly. Here you have assumed n is equals to k plus 1 2 to the power k processors, k plus 1 groups or rows, each is having 2 to the power k processors. Now rows are numbered 0, 1, 2 up to k, and processors are numbered something like that, right? Did I start with 0, 1 to k or 1 to k plus 1? There should not be any problem on 0 to k. And it is in the form, if I remember, 0, 1, 2, 3, 7, and you are telling that 1, 2, 3. this is your 4 into 8, that is 32 processors on butterfly network. Now, in order to find the sum of n numbers, now let us assume that each processor contains one element, right? And you observe that this is linearly connected, right? And also you can send the data from here to here also by log n time. This is also log n time, this is also log n time. So from any processor to another, to send the data to another processor, you take out maximum order log n time. The strategy is very simple. That your target is to bring all this data from this to this place. And wherever you are bringing, you just add it. Then the problem reduced to this zone. Right, this hub. Now, this hub will be valid or good if you can collapse this part to this side. Then your structure becomes this one. Again you divide. You bring this data from here to here. Then you bring this data here. Then you structure it here.
So, but in first step, these are not connected. Means
Which are not connected.
Means in zero row.
Zeroth. See, my point is how I will be bringing this data I will discuss. But my point is that the best way is that you divide in such a way that you can divide into the two groups. You bring this data here, then you bring this part here, then your reduction is another by butterfly, again partition, this, you bring it here, you bring down, then you get another butterfly model, sub-model. This is the idea, right? Now one thing you remember at this stage, to bring this data from here to here, it will not take more than log n time, right? Whatever way you do it. So can you prove this, that it will not take more than order log n time? The idea is that you bring this data here. Similarly, this data you can bring it here. Agreed or not? Huh? Now, if you bring this data here and add it, you bring this data and you add it. Next level, you bring this data up and add it. So all these four elements, you have done it not to, of order log n time. Now you get this data to this part. This connection exists. Order one time. Then you bring this data here, another order one time. Then this is the sub butterfly and use it again. Right? So every stage you don't need more than order log n time. And size is log n, so it takes log square n time. No, but it's very costly, n into log square n again. What we observe, that if we use the pipelining system, that the data is coming out, and then possibly you will observe that butterfly gives better result. Otherwise, most of the time, most of the processors are remaining idle. So, for example, after collapsing, as you have seen in the case of hypercube, here also it is the case that after collapsing, 50% of the processors are idle, which is, and as you keep the processor idle means your cost is increasing. You are not able to make that able to use them properly. So that is the bad part of butterfly model. like hypercube. Now let us have the sum of n number problems on linear array. There is very simple structure you have. Pi is connected with Pi plus 1, provided it exists. And the structure is P1, P2, Pn. Now, can you tell me or suggest me how to find the sum of n numbers on this type of cross connections? Suggest some method which is very good. Summation is from both sides, okay. So what he is suggesting that while you are adding this side, you start collapsing from that side also, okay. Then, what is the complexity you are expecting? Huh?
N by 2.
Log n by 2.
N by 2.
See, the data is here. Let us take one example first. 5, 1, 7, 3, 2, 6, 4, and 8. What his method is that you add this and simultaneously add this. So you get 13, 1, 7, 3, 4, 10. 14, 7, 3, 21. Right? This is the method you are looking for. So, how many steps you made? 1, 2, 3, 4. Right? Then, suppose you have 16 elements. 16 elements you need? Sure. So what is the, we are talking n by 2? So, complexity wise you are not gaining anything. Why, if I have to do, just you take this element here and add this element, that element, and so on, which takes order n time. Right? Why to make such a complex thing that you will be dividing this, into the two parts, right? Then you have to keep always a pointer to move right, which one you have to move and which one you have to send back, all those things you have to, nothing is free of cost. It will add some complexity, right? However, if I see this, number of parallel additions, right? Number of parallel additions will be less, but complexity wise you will not be gaining much. Okay? So the cost is order n squared. You have used n processors, order n time, order n square time, and order n square is the cost which is far away from the cost of humanity. However, you can think about this, whether if it is adaptive, you need order p times. In case of adaptive, right, you need p times to find the sum of p numbers. Right? Now, if I assume that there are n elements, I assume there are n elements, each processor initially contains n by p elements. Let us assume that the p processors and n elements, each processor initially contains n by p elements, and each processor is asked to find the sum of these n by p elements sequentially. So you need, if I add, I need order n by p to add n by p elements by each processor. Now you have p processor, each processor contains the sum of n by p elements. So if I collapse them and add, then I need order p times to get the sum of n numbers. So the total time Tn becomes order n by p plus order p. Agreed? This n by p is for sequential addition of n by p elements. This p is for parallel addition of p elements by p process. So cost of n elements, sum of n elements becomes order n plus order p square. Cost becomes order n plus order p square. Now this becomes cost optimal. This is cost optimal if this is order n. Agreed or not? This algorithm becomes cost optimal if this is order n. Now this becomes order n if p square is order n. That is, if p is square root of n. If p is square root of n. So basically, you have square root of n processors. Each processor contains square root of n elements. And then you perform sequentially the addition of square root of n elements by each processor. Then use parallel algorithm for finding the sum of square root n elements, which takes order square root of n. So order n, order square root of n. So total time complexity becomes order square root of n. Cost becomes order. Next one is the sum of n numbers on tree model. So, and here you have assumed that you have n processors. Pi is connected to P2i and P2i plus 1, provided they exist. So here every processor is having at most 3 connections, and if you think it is P1, P2, P3, so n can be expressed in the form of 2 to the power k minus 1, right? And height of this is, what is the height? K. Now here also it is assumed that every processor initially contains one element. every processor contains one element, right? And we are interested to find the sum of n numbers. So how to do it? Can you suggest? The collapsing technique again. So bottom up approach. You take this element and add with this, right? Both the elements come out and add with this. Similarly, these two elements comes out and add. Next step. So this contains sum of 3 elements, this contains sum of 3 elements and so on. So this contains the sum of 7 elements. This contains sum of 7 elements. Then you get sum of 3 elements. Okay? So what is the time complexity? Order k, which is order log n, right? And one thing you remember, even though we are telling that both the processors says the data simultaneously to this, but processor is only one processor, so delay will be there. Agreed or not? Because this is sending the data simultaneously. P9 cannot send the data, so P4. So this should be some delay factor to receive the data, but this is very nominal. So you have order log n time to find the sum of n elements. So cost is order n log n. So you remember this cost is increasing because the processors, most of the processors are remaining idle at every iteration. So you have to make these people busy so that the cost comes down. Now, let us see what happens to adaptive algorithms. If you have preprocessors, which form the tree model, n elements, each processor contains n by p elements. Right? So sequentially each processor performs the sum of these n by p elements, which takes order n by p times. Right? Sequentially, each processor is asked to find the sum of n by p elements, which takes order n by p time. Then these p processors are used to find the sum of these p elements on tree model, which takes order log p times. So the total time to find the sum of n elements using p processor becomes order n by p plus order log p. And that means cost becomes order n plus order p log p. So this becomes cost optimal only if p or p log p is order n. P log p is order n. That is p of the order n by log n. P is of the order n by log n. Okay? So you can verify it. But see, this finding the sum of n elements on one-dimensional pyramid model, which is same as tree model. So yes or no? Because you will not gain much through linear array on that. So you can easily design cost optimal parallelism on that. Similarly, is the case of two-dimensional pyramid model. So you can think about how to write a parallel algorithm on two-dimensional pyramid model. how to write or how to find the sum of n elements on two-dimensional pyramid model. So once you know the finding the sum of n elements, you know how to find the minimum, maximum, all those things. This same class of problems you can easily solve on parallel machines. Now we'll be discussing the special purpose parallel machine. So here we will discuss mainly sorting network. There are three types of sorting networks we'll be discussing. First one is based on enumeration sort. Based on enumeration sort. Second one is based on odd even mod sort. Third one is based on Biotronics. So these are the three special purpose sorting network that we'll be discussing. Today I will try to finish the enumeration sorting technique. Enumeration sorting network. So what is enumeration sort? First let us understand that one. Now, before that, what is sort? What is sorting? Can you tell me? What is sorting? You have n elements there, A1, A2, An. These elements are arbitrarily arranged. Okay? What do you want to do? Order in some form, either in increasing order or decreasing order. So basically I can write this is a permutation of n elements, right? Say pi x. You want to get pi y, right? Such that ai is less than equals to ai plus 1. I is greater than equals to. Right? You are looking for a permutation pi y of n elements A1, A2, and An such that ai is less than equals to ai plus 1. That is your. Now, this need not be, this symbol need not be less than equal. It is some partial ordering operator, right? It can be greater than, it may be greater than equal or something. Some relation. Now, in the enumeration sort, which we sometimes are known as rank sort, so this is a very old sorting technique. What it does, that you observe to tell whether ai is greater than aj, ai has to be compared with aj. So what happens, that you take one element, you compare this element with every other element. And you see what is his rank with reference to every other element. Then you move the data to that respected ranked element, position. That is, if I see that way, then the simple that for I equals to 1 to n, for j equals to 1 to n, if AI is greater than Aj, then rank I is increased by 1. Rank I is increased by 1. Right? Else, we don't know whatever rank you have. Now, if you know Ri is 5, that means the rank of AI is no. That means what it does, that if I find that Ri is 5, it indicates there exist 5 elements which are smaller than AI. There exist 5 elements which are smaller than AI. So rank of AI is 6. Agree? So finally you do Ri, you increase by 1 and move AI to ARI position. Move AI to ARI position. So that is a simple algorithm, you rank sort algorithms. And it is very simple to understand also. Agree? Yes. Now, here the base assumption is that elements are distinct. This is the base assumption they make, that elements are distinct. Now, what happens if the elements are not distinct? If there exists some element which are same, right? How are you going to, because this will not work in that case. Agreed or not? So how are you going to handle that one? Is it difficult task to handle? Can you suggest some method? Is it possible to modify this enumeration sorting technique if some of the elements are not distinct?
We can keep an array.
If you want,
We can keep an array in which we can keep the count of each element.
yes.
And then we can modify according to that kind. Every time that particular element occurs, then we subtract 1 from that particular position in that array. Like suppose 5 reoccurrence in particular sequence. Then I keep an array in which I put in fifth place I put 3. And every time a 5 occurs, I subtract 1 from this array, in which I am keeping the.
But how will you know that 5 occurs 3 times?
Once I will scan the whole string. But
Sure.
in this case,
What you want to do, that you scan the whole sequence first, and then you compute the frequency of each element, and then
also, but in this
I
case,
move this only if ARI is empty. Otherwise, I move it to the next empty slot.
how do you know that?
We need a after we at the end when we are storing, instead of putting it in A array, we put it in a different array, B array.
B array. And
Okay.
So we can introduce some random ordering amongst the equal elements. Like initially the positions are different. So I said that element occurring at I is less than element occurring at j. Then maybe no, like suppose AI equals to aj and I is less than j.
Now let us understand one thing. In this case, what happens if equal? First let us understand this one. If equal, what happens? It will override the but, right? So you may find in the scenario that element is here, element is here, element is here, blank, 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 element is here, blank, element is here, blank, blank, element is here. Like that scenario you will be getting. Right? That is the thing only you will be getting, nothing more than that. And these blanks you can eliminate by collapsing, that is no problem. But by that process, you will be losing this information, how many times this element occurred. That instead of it occurred 4 times, you will be writing only 1 time. So you can fill this later on also. You just scan and you fill it. Scan and you fill this value by this and so on. This can be done. Okay? But this may not solve our problem. Do you know what is the stable sort? Have you heard the term? Is quick sort a stable sort?
In which 2 elements which are occurring in which order in unsorted sequence, they will occur in the same order in the.
Yes. So quick sort is not a stable sort, because if I have the 2 elements which are, if it is a distinct, they will occur in that form, there is no problem. But if it is not a distinct, then quick sort will not give you any guarantee. The first occurred element will occur first, second occurred of the same element will occur second time. That is not the guarantee. So same thing, by doing that, that information you will be missing. You get the sorted sequence, but it will not give you the stable one, the first occurred element. Because suppose I have an element 3, along with the 3, some more information may be there. Right? 3 is the one index you got, but there may be color is there, height is there, all those things. But if you put them here, next 3 also having the different color, different height, that also is there replicating. That may not solve my purpose. Right? That's why that stable sort sometimes we need. Now you can handle this one very easily if I change this condition. The condition will be if I is greater than aj or I is equals to aj and I is greater than j, then you increase your rank. I is what? I is the index. Ith element index. If you find it is greater than the jth element in j index, then you rank, you increase. Okay? So this gives you the guarantee. This gives you the guarantee the first occurred element has the less rank with the next occurred element. Agreed?
So even while moving AI to ARI, what we can do, we can compare with value of AI and ARI. If suppose they are the same.
No, you will not get. You see, AI is, say, consider an example. A3 should move to A7 position, and A4 and these two are same. Should also showing that A7. What are you going to do?
So if our A7 is in that case A7 equal to A4.
A7 equals to?
Because we have moved A3 to A7. So
yes.
A7 will be equal to A4.
Yes.
So what we will do, we will increase rank by 1.
Whose rank?
A4's. And then move it to A8.
This and this, they are same. Now you tell me.
So if suppose repetitions are more, then this means complexity will increase.
No. So that is giving you order and die in that case. The additional payment, all those things will be coming. So the simple way to handle this is that if you find the same, then you just check the index. If I occurred first, he should be given the first chance. Right? And I and j must be distinct. There is no ambiguity in that. I and j cannot be equal. Right? So that stable thing also can be taken care on enumeration sorting. Now, the sorting network, which has been designed based on this strategy, is as follows. Okay? And these processors are arranged in the form of two-dimensional array. Okay? So, these n-square processors are arranged in the form of two-dimensional array and cross n. So, Pij is the processor. Pij is the processor in the jth column of ith row. Pij is the processor in the jth column of the ith row. Now, Pij is connected using tree connections. Along rows and along columns. What it means that Pij is connected with P2i j, P2i plus 1j provided say this and also Pi to j, Pi to j plus 1 provided they exist. Okay? That means, suppose you have P11, P12, P13, P14, P2, P21, P22, P23, P24, P31, P32, P33, P34, P41, P42, P43, P44. These are the 16 processors you have. So, connection is like that. P1 is connected with this, right? Then this is connected with this. Similarly, so this is the connection model there. It follows the tree connections if I see from this direction and also if we see from this direction. Only thing is that it becomes very complex if you have n is very large, right? But to send the data from one corner to another corner, you need how much time? Can you tell me? To send the data from one corner to another corner, how much time do you need? Tell me? Yes. Worst case, it is order log n because your n elements are there, they form a tree connection. So height is log n, right? So what from one corner to another corner, what Keras is telling, maybe 2 log n time, which sort of log n time is needed to transmit the data from one corner to another corner. So this is the network or model we are using for enumeration sort. Initially, it is assumed the elements. See, one thing you remember that what we discussed parallel algorithm, for some problems we are silent about the input part or output part. How input will be coming, that part we are not telling, because input takes huge amount of time, and this input, if we consider, then complexity may fail. Suppose n elements you have, on these n elements you want to keep in all the process. How much time you need? You need log n time, right, to broadcast the data from one corner to another, right? For one element. So log n, you have n elements to be broadcasted. You understood? It takes a lot of time. So what we assume that initially the elements are stored here, and the elements are stored here in this case. So each process, it is assumed that each process has at least 3 memory locations, 3 locations, Aij, Bij, and Rij, right? Aij, Bij, and Rij. Rij is for keeping the rank of element, and Aij and Bij to keep the elements. Initially, AI1 is xi and B1j is xj. Okay. That means here you have x1, x2, x3, x4, this element contains, and here this is x1, x2, x3, x4, this is B elements, and this is A elements, right? Now what happens that you observe that in the rank sort, every element has to be compared with every other element, right? So what happens that this A, I will be broadcasting to all the process, B will be broadcasting to all that process. So Aij and Bij are the 2 elements. Xi will be compared with Xj basically. Aij will be compared with Bij. What does it mean? Xi will be compared with Xj, right? And then you put rank Rij is 0 or 1 based on that. Then you collapse it and add it sum of Rij and keep the data here. Okay? And once you get that rank, you broadcast that element to the appropriate position. That is the idea. So first part is that you broadcast AI1 to all Aij, and similarly B1j to all Aij. So step 1 is broadcast AI1 to Aij for all j. then broadcast B1J to Bij for all I. So this element will be broadcasted to, this element x1 has to be broadcasted to all these elements, x2 will be broadcasted to this, x3 will be broadcasted to this, and so on. Because x3 is nothing but A, I, 3, 1. Similarly, this will be broadcasted. So every process will contain one Aij and one Bij. Agree? Aij is your xi and Bij is your xj. This can be done in order log n time. This also can be done in order log n time. Agree? Huh? Now, step 2, if every processor does every processor for each processor Pij, if Aij is greater than Bij, then Rij is 1, else Rij is 0. What it means? That a processor Pij has compared Aij with Bij, and if you find that Aij is greater than Bij, then rank Rij is 1, otherwise it is 0. So every processor contains now Rij's, which is either 0 and 1. Now, if I sum them this side, I get the rank of xi with reference to every other element. Agreed or not? So if it is the case, then step 3. Obtain summation over Rij over j is equals to 1 to n plus 1. This 1 is, as I did in the case of, to find his own rank if we add 1. So obtain this by all processors of each row. Now this can be done by collapsing, that is the reverse way. See, you have it has the 2 connections, then for this you have 2 connections, and for this you have 2 connections, right? Then you have, this has 2 connections, this has another 2 connections, this has another 2 connections, this has another 2 connections. So what I am telling, that this contains 0 and 1. By 3 connection model, you send the 2 elements, you send it here and add it. So you get the sum of 3 elements here, sum of 3 elements here, sum of 3 elements here. Now you send these 2 elements to here, and you get the sum of 7 elements. These 2 elements you send it here, sum of 7 elements. These 2 elements you get, and this you get sum of 15 elements. Right? And log n time is sufficient to collapse this thing to get these elements. So you need order log n time to compute this one by collapsing method. Agreed? Any ambiguity here? So once, and let it be, say, let it be j, not j, some, say, let us assume that this is equals to L. This is equals to L. What it means? There will be rank of xi is L. Now, if I have to store it, the step 4, that move A AI1 to AL1 by all processors of ith row.
So where are we storing this L?
Huh?
Where are we storing the L?
So this sum of this, you put it in RI1. You store it in RI1. It is in RI1. Because that is this rank element here. RI1.
So L is RI1.
RI1. Right? Now move AI1 to ARI1 area. Right? So from here what you have to do? You have AI1 and you have AL1. So this data may go to some AM1. This may move to AM1. This data has to be brought here. This one has to be brought here. This will move out. Obviously, because the one position, only one element will be there. Now, how to bring this element to this position? That is the problem. So, in order to do that, you first, through tree connection, this direction, I can move it to AII. Using tree connections, I can move it to AII. Agreed? If I can move it, I can move it to ALI using column connection. AI1 move to AII, AII moves to ALI using column connection, column tree connection. From there, using collapsing method along the row, I can move the data to LI1, AL1. Yes or no? First, I move the data from here to here, from this to this, this to this. Right? Yes?
For all the values.
Only one value, you have RI. Huh? See, this contains L.
Right.
So this moves to AII.
But the value that was already in L, even that has to be moved somewhere else.
Yes, that will go to this. So this will move to ALL. Then AML. Then AM1. Right? So this takes order n time. This takes order n time, right? Order log n time. So this takes order log n time. So you observe the total time complexity is order log n. Using order n square processor, cost is order n square log n to sort n elements. Order log n time, very fast. Order n square processor, but cost is order n square log n. The bad part of it is that the model is very complex. Model is very complex. Every processor is having in row direction 3 connections, in column direction another 3 connections. Agreed? At most. Now the problem remains, or you have to try at home, is that there is no way, while AI1 likes to send the data to AL1 and AL1 wants to send the data to AM1, there is no conflict. Right? If there is a conflict, then there will be a chaos. So how to prove it? While you are sending AI1 to AII, there will be only one element who will be sending the data to AI1 to AII. There is no way AL1 will conflict with AII because that will go to ALI using the other tree connections. Agreed? Now when you send the data from here to here, and you are sending the, so you are using different, because this is ALL and this is AII. You are sending the different column connections to send the data from here to here and from here to here. Similarly is the case. So there is no possibility of having any conflict between the two elements while sending the data from one corner to another corner. Okay? So any doubt in this? Or you please go through first, and then this is available in Salim J. Ekal's book on sorting and